Welcome back. In this video, I'm going to describe some methods for solving systems of nonlinear equations. I'm going to warn you that there's no general strategy for these. There are some systems of nonlinear equations that are essentially impossible to solve, at least algebraically, at least without approximations and getting something that's kind of a solution but not really. I'm going to focus on systems of nonlinear equations that have solutions and whose solutions are relatively easy to obtain. And what I mean by that is you don't need to use special functions. You don't need to use anything particularly high-powered. There's two major techniques that are used for solving these systems. One is based on substitution, and the other one is based on something that I call the case method. They're kind of related to each other. Oh, and there's a third way I should mention that once in a while, if the stars align, you can use elimination. So subtracting some multiple of one equation from another equation. Anyway, so let's look at some examples of systems of equations. We have this set of nonlinear equations in terms of x and y, and the goal is to solve for x and y together at the same time to find what combination of x comma y values, if plugged into the first equation and into the second equation, will make left-hand side equal right-hand side. So looking at this, we could, for example, take the first equation and rearrange it and get y all by itself. Or we could take the first equation and rearrange it, and I don't think we can easily get x all by itself. So you think about strategies like this. Can you isolate for one variable in terms of the other variable in either equation 1 or in equation 2? If you can do that, then that's probably a good way to proceed. So what I notice is that inside the first equation, if we, let's see, add 4x to both sides, so 6x squared plus, and subtract 6x squared from both sides, so 2y is equal to 4x minus 6x squared. Then divide both sides by 2, we get y equals 2x minus 3x squared. What we can do with this is we can substitute it into the second equation. So I'll do that here. We have minus 9x to the power 4 plus y squared. So plus 2x minus 3x squared, all squared equals 0. This expression is just strictly in terms of x. Next thing I'm going to do is I'm going to FOIL. Power 4. I'm going to FOIL out that bracket. We have a bracket of stuff times itself. So first times first, outside times outside, inside and inside, last times last. So we have 2x. Well, I'll write out the terms because I'm going to get confused if I don't, because they're strange. So negative 9x to the power 4 plus I have a 2x times a 2x, that'll be 4x squared. A 2x times a negative 3x squared, that'll be negative 6x to the power 3. Another negative 6x to the power 3 from the inside times the inside, and then last times last plus 9x to the power 4 is equal to 0. We do get a nice cancellation. We get the first and last term on the left canceling. Negative of something and the positive of the same thing. And then from the leftovers, we can common factor. Or actually, let's collect like terms. Let's do that. Collecting like terms, 4x squared minus 12x to the power 3 is equal to 0. Now we can common factor. I'm going to common factor of 4x squared out from these. We'll have 1 minus 3x left. I'm a little bit paranoid that it appears that a fraction is coming out. Let me just double check I didn't mess something up. Plus, that's a plus sign, okay. And then we have plus y squared. I'm just gonna it's worth making sure that there's no horrible mistakes. and then divide by 2. That looks fine. Plug it in. That looks fine. Yep, I guess. Okay. So we look at the two different ways that this expression can be 0. Either 4x squared is 0, which means x is equal to 0, or 1 minus 3x is 0, which means 3x is equal to 1. So x is equal to 1/3. Okay, so we have two solutions for x. For each of those, we go back and get the corresponding y value. So if x is equal to 0, then y is equal to 2x minus 3x squared. So 2 times 0 minus 3 times 0 squared, which is 0. So one solution is 0, 0. Let's check the second one. 2 times 1/3 minus 3 times 1/3 all squared. So 2/3 minus 3/9, which is 2/3 minus 1/3, which is 1/3. So the other solution is 1/3, 1/3. Now what we should do when solving a system of equations, if you have time, is make sure that they work. Plug each set into both equations and make sure left side is equal to right side. So it's easy to check the first one, 0, 0. Like all the terms there are terms that involve x or y. There's no constant pieces. When you plug 0, 0 in, you get 0 is equal to 0 for both equation 1 and equation 2. For 1/3, 1/3 is a bit tougher. So we have 6 times 1/9, so 6/9 plus 2/3, so 4/3 minus 4/3 is 0, so the first equation is good, and then negative 9/81 plus 1/9 is equal to 0, so negative 1/9 plus 1/9 is 0. So yeah, both of those equations work for these two solutions, so no mistakes were made anywhere along the way. Okay, here's a different one, looks pretty horrifying. And this is one of the ones where the stars align. And it's rare, but it does happen. Each equation contains a mixture of x's and y's, and there's no nice thing that you could do to factor them. I guess you could rearrange the first one and rewrite it as 2xy squared minus 2x squared y is equal to 4x. You could do that. But I'm going to add these equations together. Add equation 1 and equation 2. This is like the process of elimination. I'm adding them because if I line up this term and this term, I line up this term and that term, subtraction will result in those pieces canceling. Now if there was different numbers in front of each, and they were, let's say, plus 6x squared y, and the other one was minus 6xy squared y. Yeah, if it was 6 instead of a 2 in the second equation, then I would take the first equation, multiply by 3, and then do the addition, make it match. So it's just like what you would do for linear systems for the method of elimination. Anyway, so let's add them together. We have an x squared plus a 2xy squared minus a 2xy squared plus a 2x squared y minus a 4x minus a 2x squared y plus a 4x minus a 1. And we get lots of stuff that cancels. We have 2xy squared and negative 2xy squared. We have plus 2x squared y and minus 2x squared y. And we have a 4x and a 4x. And I forgot the right hand side equals 0. adding the right-hand sides together. 0 plus 0 is 0. Now, what we have left is x squared minus 1 is equal to 0, which has two solutions. X is equal to 0, and x is equal to, no, not 0. X is equal to 1, and x is equal to negative 1. So each of those squared minus 1 is equal to 0. Okay, now what we do is we can plug this result either into equation 1 or into equation 2 for x and get the corresponding y values. So I'm going to take this first value and plug it in for x. I'm going to plug it into the first equation only because it has fewer terms. And then we'll do the same thing for this guy. This is x is equal to negative 1. We'll plug that one into equation 1. We have to do them separately. All right. So we have negative 2 times 1 y squared plus 2 times 1 squared y plus 4 times 1 is equal to 0. And we can simplify negative 2y squared plus 2y plus 4 is equal to 0. I'm going to divide both sides by negative 2 so that the coefficient in front of the quadratic term, the y squared term, is 1. So y squared minus y minus 2 is equal to 0. And then I'm going to factor into two linear terms. The mystery numbers in the brackets must multiply together to give negative 2 and add together to give negative 1. So negative 2 and positive 1 will be the factors. And then this tells us that y is equal to 2 and y is equal to negative 1 are solutions. We have two critical points from this case. So I'll make a box of critical points in here and contribute to the box. We have the point 1, 2, and we have the point 1, negative 1. And those contributions both came from x equals 1, from that solution to the line up above the red. Now we're going to do the same thing for the other situation, the other solution for that. If x is equal to negative 1, what happens? So now I'm going to sub it in. We have negative 2 times negative 1 times y squared plus 2 times negative 1 squared times y plus 4 times negative 1 is equal to 0. Simplifying 2y squared plus 2y minus 4 is equal to 0. I'm going to divide both sides by 2. Y squared plus y minus 2 is equal to 0. We're going to factor it again into two linear terms, or at least we'll try. Y and y. I want the numbers to multiply to give negative 2 and add to give positive 1. So this time it's plus 2 and minus 1 as our factors, and this admits two different solutions. Y is equal to negative 2 and y is equal to positive 1. So this also contributes two critical points to our box. So that was negative 1, negative 2, and negative 1, positive 1. So 4 total critical points. And they have to be paired up appropriately. We can't take the x equals 1 solution and pair it up with y equals negative 2 or y equals 1. Those two y values came from x equals negative 1. So when we pair things up, we have to be careful. Okay, here's a different format. Let's see. we have x squared plus something is equal to 0, and x squared plus something else is equal to 0. And we could isolate the... Yeah, there's not really much we can do without throwing away solutions, except use the case method. So inside this first equation, what I'm going to do is I'm going to factor it and make two different cases. This is a new type of method of solving, kind of. So I'm going to common factor an x out, and we have x plus 4y is equal to 0. There's two different possible ways that this statement can be true. Case 1, x is 0. We'll have 0 times whatever is there equals 0. Case 2 is that x plus 4y is equal to 0, which means that x is equal to negative 4y. I'm going to circle those. X is 0 for case 1, x is equal to negative 4y in case 2. And what I'm going to do with these is I'm going to take each and plug them in to the second equation. What will happen is the second equation in both of these cases will have one variable only. So we're going to plug case 1 into equation 2. So it starts off x squared plus 9y squared minus 225 is equal to 0. So in case 1, we are replacing x with 0. So we have 0 squared plus 9y squared minus 225 is equal to 0. I'm going to divide both sides by 9. Is that possible? So if I divide both sides by 3, let's see. What's 75? 75 times 3. So 15. Yeah, 225. Oh, it is. Okay. So we're going to divide both sides by 3. We'll have 3y squared minus 75 is equal to 0. Then I'm going to divide by 3 again, because I couldn't divide by 9 in my head. Couldn't do it, but I can divide by 3 twice. Okay, so y squared minus 25 is 0, which has two solutions, which has y is equal to 5 and y is equal to negative 5. Each of those gets paired up with x is equal to 0. So that's where the case came from. So I'll make a box of solutions at the bottom that this will contribute to. We have 0, 5 and 0, minus 5. Now we're going to do the second case. Plug case 2 into equation 2. So we have x squared plus 9y squared minus 225 is equal to 0. Now I'm going to replace the x with a negative 4y. So negative 4y all squared plus 9y squared minus 225 is equal to 0. When we square something in brackets, if we have a, let's say a times b all raised to the power of 2, we can apply the power of 2 to both pieces separately. We get 16y squared plus 9y squared minus 225 is equal to 0. Collect like terms, 25y squared minus 225 is equal to 0. And we just saw that 225 divided by 3 twice, so divided by 9, gave us 25, and that means 225 divided by 25 has to give us 9. So y squared minus 9 is equal to 0. And we get two solutions, y is plus and minus 3. But it's not as neat as the last one because we don't know what x is yet. All that we know is that x is equal to negative 4y. So we have to go back to that and sub this in. So negative 4 times 3, negative 12 for that one. And negative 4 times negative 3, so positive 12 for that one. Now we'll add these solutions to our box. So we get the x value of negative 12 paired with the y value of 3. And we get the x value of positive 12 paired with the y value of negative 3. So we end up with 4 solutions. Just as a warning, sometimes when you use the case method, one of the cases, or maybe even both the cases, will not yield a solution. You'll get something like y squared plus 9 is equal to 0, which is impossible. There's no solution for that in terms of real numbers. All right. So now we're going to go back to the full examples of these maximization questions. Find the max value of this function. And they give us fx and fy. So step 1 is done. Find fx, fy was given. Step 2, solve the system. So here's your system. F sub x equals 0, f sub y is equal to 0. So we have y plus 4 minus 2x is equal to 0, and the other one is x plus 1 minus 2y is equal to 0. I'm going to isolate the first equation for y. If you want, you can isolate the second equation for x. I'm choosing in this way to avoid fractions. Isolate for y. So y is equal to 2x minus 4. And then we'll do what we did in similar examples previously, is I'm going to plug that in. So we're going to replace y with that. So we have x plus 1 minus 2 times the y value, 2x minus 4, is equal to 0. So x plus 1 minus 4x plus 8 is equal to 0. And then collect like terms, negative 3x plus 9 is equal to 0. And that tells us that x is equal to 3. Now we need the y value. Y is equal to 2x minus 4. So 2 times 3 minus 4. 6 minus 4, which is 2. And that tells us our critical point. We only have one of them. It's 3, 2. Okay, step 3. We'll get the second derivatives. It's kind of silly in this example to do the entire thing because we found one critical point. It's telling us to find the max value, but I'm paranoid. F double x, the x derivative of f sub x, we get 0 plus 0 minus 2. So we get negative 2. fxy, we take the y derivative of f sub x, we get 1 plus 0 minus 0, we get 1. And f double y, we take the y derivative of f sub y, we get 0 plus 0 minus 2, so negative 2. Step 4, we can create the diagnostic function. Capital D of x comma y is f double x times f double y minus fxy all squared. And it's not a very interesting diagnostic function. It's negative 2 times negative 2 minus 1 squared. So 4 minus 1, we get 3. It's always positive. Step 5. Capital D evaluated at the one critical point that we found. D evaluated at 3, 2 is equal to 3. It's positive, so it's not a saddle. Then we can do step 6. F double XX at 3, 2 is negative 2. So it's negative. It is concave down. That means it's a max. And then step 7, find the value of the function. So the value of the function at its max is f evaluated at 3, 2. So that'll be 3 plus 1 times 2 plus 4 minus x squared, so minus 3 squared, minus y squared, so minus 2 squared. And then simplify, we have 4 times 6, 24, minus 9, minus 4. So I think that's 11. And that'll be our final answer. So option C. And in truth, we do not need to do steps 3, 4, 5, and 6. Because there was only one critical point, and the question kind of gave us a hint, find the maximum value of the function. We just need to plug in 3, 2 into f of x, y. All right. Another type of example, I think we already saw something, we saw something like this in multiple choice format. Here it's not multiple choice format, it's asking us to draw some conclusions about the critical points. So we're told that these are critical points. That's given to us. So we are told that f sub x of a comma b equals 0, f sub y of a comma b is equal to 0 for each point. That's what it means for these to be critical points. If we weren't told that information, we just said, hey, here's some points, we couldn't answer this without having the first derivatives to make sure that they're critical points. All right. So we're skipping right ahead to, I forget my numbering, we're skipping right ahead to step 5. Steps 1 to 4 were done for us. Diagnose critical points. So we're going to plug each critical point into the diagnostic function that was given. So capital D evaluated at 2, 2. We're going to have 4 times 2 times 2 minus 2 times 2 plus 2 times 2 minus 6 all squared. So I'll have 16 minus 2 squared, which is positive, so it's not a saddle. So that's all it does, is it filters out saddles. Now we do f double x at 2, 2. F double x is given. F double x is equal to 2 times y. So here we're going to have 2 times 2, which is 4, which is positive. That means it's concave down. Oh, sorry, concave up, which means there is a min at 2, 2. Okay, now we check the next critical point, D evaluated at 6, 0. So 4 times 6 times 0 minus 2 times 0. Well, I should put it in the right order. Oh, it is, yeah. 6 times 0. And then minus 2 times 0 plus 2 times 6 minus 6 all squared. So we'll have 0 minus 12 minus 6, so 6 squared 36. We have something negative, so that means it's a saddle at the point 6, 0. Okay, next critical point, we're going to check 0, 6. So 4 times 0 times 6 minus 2 times 6 plus 2 times 0 minus 6 all squared. We get 0 minus 6 times 6 again, so 0 minus 36. Negative, so it's a saddle point at 0, 6. And we have one more point to check. D evaluated at 0, 0. So 4 times 0 times 0 minus 2 times 0 plus 2 times 0 minus 6 all squared. We get 0 minus 36, which is negative, so it's also saddle. Saddle at 0, 0. So as a summary, this function has a min and 3 saddles. Didn't ask us for that summary, but I'll just point out, just because. There's 3 saddle points. Okay, and one more example. So this is a question that's requires a little bit more care. The previous one told us that the points given were critical points. This one doesn't. So we have to check, are these just random points that were made up? Maybe they're not even on the curve. I shouldn't say that, they're on the curve, but maybe they're not even, interesting. They're just random. Someone just picked some random numbers. I say they're on the curve because they're in the domain. So that means they have to be on the curve. The function is given in the bottom in the blue. Okay, so we are skipping step 1, taking the first derivatives because they're given. We're skipping step 2, which is finding the critical points by setting the first derivatives to 0. Instead, we're going to check each critical point. So it's kind of step 2. Check we're going to check each point to make sure it is critical. Okay, so f sub x at 0, 0 is equal to 6 times 0 minus 3 times 0 squared, which is 0. F sub y at 0, 0 is equal to 6 times 0 plus 2 times 0, which is 0. So far, so good. So it's critical. Okay, now we're going to check the next pair. F sub x at 1, negative 3 is equal to 6 times negative 3 minus 3 times 1 squared, which is negative 18 minus 3, which is not 0. So not a critical point. We don't even have to check f sub y. As soon as one of them fails, it doesn't matter. So 1, negative 3 is not a critical point. And then the last point we'll check, f sub x at negative 6 comma 18. So I'll have 6 times 18 minus 3 times negative 6 squared. So that's going to be, let's see, 60 plus 48. Rewriting 18 as 10 plus 8, and then distributing 6 times 10 plus 6 times 8, and then minus 3 times 36. You know what? I'm being an idiot. There's a simpler way to do this. I'm going to common factor out 6 from this. So I have 6 times 18 minus 18, which is 0. And then the next one, f sub y at negative 6 comma 18, that will be 6 times negative 6 plus 2 times the y value, 2 times 18. So I'll have negative 36 plus 36 is 0. So yep, that's a critical point. I guess it's kind of a sad thing, because if it wasn't a critical point, we could just stop, right? That's the best outcome if you're doing a test. Not a critical point. The second best outcome is a saddle, because then you don't have to check the f double x. So negative 6 comma 18 is a saddle point. This is not a saddle point. Sorry, is a critical. I'm screwing myself up. Is a critical point. Now we have to do the next step, create the diagnostic function. So the second derivatives were given, that step 3 is done. Now we're going to do step 4, d of x comma y, and it is negative 6x times 2 minus 6 squared. So negative 12x minus 36. Then we're going to plug in the points that we found. So this is step 5. D evaluated at, what was it? 0, 0. So let's see what happens. We'll get negative 12 times 0 minus 36, which is negative. So there's a saddle point at 0, 0. And then the last one, the last critical point we have to check. We don't have to check 1 comma negative 3 because it's not a critical point. We don't have to plug it into D, but we do have to plug the other one. Let's see, negative 6 comma 18. So it's negative 12 times negative 6 minus 36. So 72 minus 36 is positive. So it's not a saddle. If it's not a saddle, now we have to check the concavity. So step 6. Negative 6 comma 18. Or not of, check the concavity at that point. So f double x evaluated at negative 6 comma 18. F double x is negative 6x. We have negative 6 times negative 6, which is positive. That's concave up. That means there's a min at that point. Negative 6 comma 18. Whew. A lot of work. And this question just isolates for that part of the calculation.